Welcome to my channel Phi Concepts CHM. This is the second part of the field effect transistor series. Here we will see about the drain curve and transconductance curve. Characteristic curves and parameters. First we will see about the drain curve. Drain curve is the variation of drain current ID with a drain source voltage VDS. So these are the drain curves. This is ID versus VDS. When VGS is equal to 0 volt, that is no voltage is applied to the gate, that is the top curve. The drain current increases rapidly first. When VGS is equal to 0 volt, we can see that that ID is increasing rapidly. Then levels off and becomes horizontal. So here it has become horizontal. Here the depletion layer is minimum. Hence current flowing through the drain is maximum. Now as VGS is increased further, that is in a negative manner, from 0 now it has become -1 volt, then -2, -3, -4, that way the channel becomes narrower and the current will drop. Now we'll see the different parameters. First is a pinch off voltage, which we denote as VP. It is a voltage where the highest drain curve changes from almost vertical to almost horizontal. So this point here, it is VP. Ohmic region. So that is indicated here. This is the ohmic region. Almost the vertical part of the drain curve, this part. Here the current is proportional to voltage. Here the FET acts as a resistor with the value given as RDS equal to VP upon IDSS. IDSS, that is when VGS is equal to 0 volt, this is IDSS, where IDSS is the current from drain to source with shorted gate, that is VGS is 0 volt. Constant current or saturation region, that is this part. We also can call it sometimes active region. It is almost the horizontal part between the pinch off voltage and the maximum voltage VDS max. Here the JFET acts as a current source. Then the breakdown region. This is the breakdown region. If VDS exceeds a critical value, the drain current suddenly increases due to the breakdown of the reverse biased PN junction. Here now the FET should not be operated in this region. Cutoff region. So this part, this is a cutoff region. As the negative voltage applied to the gate increases, width of the depletion region increases. The drain current will fall, it will decrease, and at a particular gate voltage, the drain current falls to 0. That particular gate voltage is called as gate source cutoff voltage. We denote it as VGS off, and it is found that VGS off is equal to minus VP. Next is the transconductance curve. This is the transconductance curve. It is a plot of ID versus VGS at a constant value VDS. This is ID versus VGS at a constant value VDS. It is a non-linear curve, you can see, and here the current increases faster as VGS approaches 0. So here you can see current is high here. You can see that the current is increasing and it becomes maximum at VGS is equal to 0. So there are two important points to look at here, that is IDSS and BP. This is IDSS and this point we can call it as BP. Rest of the curve is obtained from the Shockley's equation, which is given as ID is equal to IDSS into 1 minus VGS upon VP the whole square. So when VGS is equal to 0, so when VGS here it is equal to 0, we get ID is equal to IDSS. When ID is equal to 0, if you put ID here 0, then what we get is 1 minus VGS upon VP is equal to 0, and that will be VGS is equal to VP. Sometimes this VP is written as VGS off. We had seen in the earlier slide that VGS off is equal to minus VP. Thank you for watching this video.